Uh, Good morning or good afternoon or good evening, everyone, and thank you for joining us. Today, we have a great pleasure to welcome Peter Cawood from Monash University. So Peter is has a very nice position at Monash University. He's a laureate fellow of the Australian Research Council. And today he's going to talk to us about the evolution of the Earth. And Peter, the floor is yours.
Thank you very much, Catherine. And it's a pleasure to be here. So welcome, everyone. I think this first slide captures in part what I'm trying to talk about today in terms of the title. The title is Earth's Tectonic Modes. And so what I want to deal with is clearly plate tectonics is the current tectonic mode, and that is shown nicely by the diagram in front of you there of the Earth, present-day Earth, this beautiful planet we live on. But it hasn't always looked like this, has it? And that diagram, or that hot body in the background, shows what we think the Earth might have looked like, or the proto-Earth looked like when it first accreted from the solar nebula. And so has plate tectonics, which is the current tectonic mode, always been in operation since the Earth first formed, or have other modes been also in operation at various times? And it's a question that, we argue about. We don't know the answer to, and we are still collecting data, thinking about the problem, assessing our ideas, etc. And so I'm going to present some information today, which is really based on a paper that you can see in the bottom here was published in Reviews of Geophysics right at the end of last year. And I do want to acknowledge my various co-authors that are listed there, without whom this paper would not have been possible. So this diagram attempts to show that plate tectonics is the current mode, as shown in this bottom diagram, and also known as active lid mode. And what you can see here is that the characteristics of plate tectonics are rigid plates with rapid changes in surface velocity, or in 2 dimensions, or in 3 dimensions, it would be angular momentum, with narrow plate boundaries, narrow zones of deformation represented by trenches, represented by spreading centers, represented by transform faults. Now, we think when the Earth first formed, we may have had quite a different mode. That picture I showed in the previous diagram with that hot orb as the Earth first accreted, we had the magma ocean, and then once the Earth cooled, we think we may have had a stagnant lid mode. And a stagnant lid mode is one in which you have a lithosphere and a mantle, but there is no coupling between them. You have a convecting mantle, but no coupling with the lithosphere, so there's no significant surface velocity. And I suppose there are 2 types of stagnant lid. One is in which you have a convecting hot mantle, and the other, Venus might be a typical example of that, and one in which you have a cold, essentially solidified mantle situation. Now, in between, I've shown here what I refer to as a squishy lid mode, in which you have some coupling between the mantle and the lithosphere, but the lithosphere isn't rigid. So you get broad zones of deformation, essentially corresponding to protoplate type boundaries, and the velocity of the plates internally is variable. What does that mean? That means that there are broad zones of deformation. The plates are not rigid, they're deforming internally. So I suppose what I'm going to try and do today, and you can be the judge at the end, is try and convince you that plate tectonics has not always been the modus operandi of the Earth, and that this squishy lid mode may have been important for significant times during the early history of the Earth. So let's start with this diagram. And the question, when did plate tectonics start? And as I mentioned, there's a whole range of possibilities. And I'm sure each of you listening today probably has your own view, and it may well be different from mine. That doesn't mean that you're wrong and I'm right. It means that probably we haven't convinced each other yet when plate tectonics did start. One of the things in geology, and one of the arguments that's often used, is what's called deductive reasoning. So inference to the best explanation, and that's represented by that well-known phrase, if something looks like a duck, swims like a duck, and quacks like a duck, then it probably is a duck. And that's, pretty straightforward and simple to follow. And that's what we really apply in terms of plate tectonics on the present day, but extrapolating it back through time. In other words, on the present day, we have rigid plates, we have focus zones of deformation, whether they be extensional or compressional, and they're marked by earthquakes. So they're the kind of characteristics in terms of, looks like a duck, we have rigid plates, swims like a duck, we have extensional and compressional boundaries, quacks like a duck, we have earthquake focal mechanisms that help us locate these plate boundaries. As we go backwards in time, of course, the record isn't quite so complete. And so we only have parts of that evidence. So if we just have a duck's bill, is that still a duck? And obviously, it may not be in terms of the example I've shown there. So when you've got an incomplete data set, incomplete rock record in terms of the Earth, then it becomes harder to use deductive reasoning. And of course, as we go backwards in time, this is what we really have. We don't have the duck left at all, really. We have perhaps these shadows of the duck, perhaps a little fragment of the duck, and this is what the rock record is for the early Earth. It's very incomplete. We have proxies of processes that go on. We don't actually have direct record of the process. We have a proxy representation of it. So that is part of the problem. And another way of looking at it, that was my example, Tarascaria had this example, and an egg doesn't look like a chicken. So it doesn't matter how many chickens you see, you can see thousands, tens of thousands, to assume that a normal-sized chicken originated from a very small chicken is not the right approach to take. It originated from an egg. So the past and the present can be quite different in that sort of scenario. So that gets back to this viable tectonics modes. This is what we see today. Can we extrapolate these features back in time? How far back can we extrapolate those features? Or are there other features that have been operating that suggest that the past wasn't exactly the same as the present? So that's really the aim of what I want to try and approach today and try and convince you of. So yes, the past is different from the present, and we see that in lots of different ways. Certainly in terms of the superficial Earth, the biosphere, the atmosphere, the oceans have all changed in composition or in character with time. And linked to that, or we think linked to that, there have been changes in the nature of the continental crust, the composition. We think also in the volume of the continental crust through time, and I would argue the tectonic modes that have operated through time and helped produce those continental volumes, those continental compositions. Why? Well, I think mantle temperature has played a key role, and mantle temperature has been decreasing since the Earth first accreted from the solar nebula. So that's a first order constraint that has to be invoked and dealt with. So I talked about changes in the continental crust. I talked about changes in its composition, changes in its volume. Today, of course, when we look at the continental crust, we have classic continental material, perhaps an average thickness of 40 kilometers. And more importantly, we have this bimodal hypsometry of the Earth. We have oceanic lithosphere, oceanic crust, and continental crust. Dense, relatively felsic, relatively buoyant. For the early Earth, when it first accreted and when the magma ocean first solidified, we had probably a large mafic crust covered by a global ocean as the magma ocean crystallized. So at some stage in between those two, we've differentiated, or we've developed the continental lithosphere. We've developed a bimodal type oceanic or mafic, early mafic crust and an early cratonic crust. So the question might be, once we started to develop these types of crust in the Archean, in other words, cratonic and mafic, was that produced by plate tectonics, or was it produced by some different process? And the other thing, just in terms of characteristics of the Archean crust and the modern crust, is to look at their compositions. And a good way of looking at it is silica content. We know that the modern continental crust is essentially, its bulk composition is that of calc-alkaline andesite. All right, and you see that when you look at compilations of elemental abundances for the modern Earth. So here's ones for modern convergent plate margins. Here's a more detailed one just for Andean type margins. But it doesn't matter what you do. You see this broad, overall unimodal silica composition focused in around 55 to 60 for all convergent plate margins, and more around 60 if you're just looking at the Andes. Now, if you do the same kind of compilation for the Archean, it's quite different. It's much more bimodal in character. You have more silicic rocks at around 70% and more mafic rocks at around 50. The mafic component may be oversampled. People tend to sample greenstone belts more than the felsic rocks in the Archean cratons, but you get the point that there is this bimodality in the composition. And again, what's the relationship to tectonic mode? We know the relationship to tectonic mode with these sorts of lithologies, but what is it with respect to the Archean cratons? Similarly, volumes of continental crust through time. Today, we have 100% continental volume of the crust, of continental crust. When the Earth first formed, it was 0. How do we get from 0 to 100%? Well, as you can see, different people have different opinions. But I think the bulk of the present day opinions is of this sort of progressive increase through time. Some might have it more rapid initially and then tapering off, but overall an increase through time. And again, what's the relationship of this change in volume of continental crust with tectonic mode? And here are some different plots, again, just coming back to this concept of decreasing mantle potential temperature, some different estimates of mantle potential temperature, and again, there's uncertainty. In fact, I would say one of the keys to resolving some of our disputes or uncertainties about processes that have operated on the Earth is to get a better handle on mantle potential temperature through time. And so we all agree that it was hotter back when the Earth first formed in the 15 to 1600 degree type range. It's more around 1350 today. But the rate at which we have cooled to reach that point is still being debated, because different data sets, different types of data are brought to bear in establishing those temperatures. So, okay, secular cooling of the mantle is probably a first order control we have to consider. Why? Because temperature affects mantle viscosity. That in turn imparts an effect on lithospheric rheology and probably composition and geodynamics. And so understanding how we moved from a mafic early crust when the Earth first solidified from the magma ocean to this differentiated continental and oceanic crust that we have today that we can pretty clearly associate with plate tectonics is a primary problem. So I'm going through a long introduction here, and it's really to kind of get us all thinking about the same sorts of problems and on the same page. So with that in mind, what I want to do is talk about what is plate tectonics. And you think, well, I know what plate tectonics is. We all know what plate tectonics is. And here's a typical first year geology text or even a high school text showing you what plate tectonics is. The Earth is divided into rigid lithospheric plates. They're moving about Euler poles, and they're moving across linked continuous boundaries, whether they be convergent, whether they be divergent, whether they be transformed in places, all right? And that whole system is sustained, it's ongoing, and we have ridge push, potential energy from the ridge, from the height of the ridges, pushing off the spreading ridges, and then we have phase transformations in the slab as it's subducted, driving slab pull, as well as just the density of the slab relative to the mantle. And so this forms this global system. The problem with that, with that definition, is that it's a kinematic definition, all right? And as we move backwards in time, sure, we can extrapolate that kinematic definition through the Cenozoic into the Mesozoic, but it's largely tied to the presence of mid-ocean or of oceanic lithosphere. And prior to the Mesozoic, prior to 200 million years, we have no modern-day oceanic lithosphere preserved. So we've lost 60% of our reference frame, from the current surface, as we go backwards in time. So that's part of the problem in terms of establishing when plate tectonics started. We've lost that reference frame. And yeah, we can go back and everyone agrees that, plate tectonics was operating at least in the Neoproterozoic, but then features that we see preserved in the rock record, which is in the continental crust, people dispute and interpret differently. And so once we get through the Proterozoic and certainly into the Archean, there's some uncertainty. One thing I want to try and convince you of is that a prime requirement of plate tectonics in terms of this definition I've given here is we have rigid lithosphere. So how far back can we go and be confident that the lithosphere is rigid? So I want to try and argue that, in fact, as we go back with higher mantle potential temperatures, the nature of the Earth in terms of that time, in terms of the characteristics of the asthenosphere, probably more higher degrees of partial melting in the asthenosphere. This impacted viscosity in the asthenosphere. It impacted rheology in the continental crust. There would have been more widespread magmatism in the continental crust. And so I consider that the nature of the plate boundaries or the lithospheric boundaries were much more diffuse, and we had ultimately a non-rigid lithosphere, the kind of terrains we see in the classic Archean cratons. So what I want to do now is go through some key points, mainly focusing on the late Archean. I'll come to the early Archean and the Hadean later on, but outline some general features on when we can say we had rigid crust and lithosphere, focused deformation. What do sedimentary basins potentially tell us about that kind of discussion? What does geochemistry tell us? Many of you in the audience may know more than me on that. The metamorphic record and the paleomagnetic record. How can we use those to try and understand when plate tectonics started? And I'm going to give you some ages on when I think these things are important, but I want to point out that these are minimum age constraints. And so other people, it doesn't necessarily say when plate tectonics started. It must have started by these dates, but perhaps it also started earlier. And the other important problem is that we often deal with general type issues. When did plate tectonics start? But we're often dealing in the early Earth with specific records, individual outcrops, individual parts of cratons or whatever. And what we're trying to do is make global predictions from that. And that's very difficult often, to take local data and apply it globally. So that's just something to bear in mind. But what I want to do with all this information here is try and reach a point where I think we have evidence for the assembly and dispersal, i.e. lateral motion of lithosphere, but it didn't happen instantaneously. I can't just click my fingers and say, at this point in the geological record, plate tectonics started. The transition between a non-plate tectonic mode and a plate tectonic mode was probably protracted. It was transitional. And it took a while before we established this globally linked and sustainable system that characterizes plate tectonics. Okay, rigid lithosphere. Well, what's a criteria one can use to recognize rigid lithosphere? And dikes and basins are two key criteria that I want to try and convince you of. And I don't mean walking up to an outcrop and seeing a dike cutting through it. Yes, that outcrop is rigid to have a brittle dike, to have the rock brittly fractured and a dike injected along that fracture. What I'm talking about are dikes that transgress entire cratons. So here's the Zimbabwe craton, okay, in southern Africa, scale here of 100 kilometers, and the Great Dike, dated at 2.57, traverses the entire craton. Here it is in an air photo. You can see it's incredibly wide relative to the landform and can be traced for hundreds and hundreds of kilometers. And one can look elsewhere and one can see in the North Atlantic, individual regions, perhaps at 3.5, certainly by 2.5 across the entire craton. Here's the Yilgarn in Western Australia, and these red lines are dikes that can be traced across the craton. And importantly, they transgress across earlier structures within the craton. So these are clearly late. They're dated at 2.4, and so we know that the Yilgarn craton was a rigid block by this time. And this diagram here is a compilation diagram I've made for the different cratons, Superior, Karelia, North China, Zimbabwe, etc. And these little stick symbols on the diagram are when we have regional scale dikes across them. And you'll see most of the cratons, we can recognize large scale dike systems. Interestingly enough, there seem to be quite a few at around 2.5 or 2.45 within these cratons. So that's important. Okay, so we have brittle fracturing of the lithosphere. So that's evidence that we probably were dispersing continental blocks to produce those brittle fractures. And more importantly, people have argued that some of these dike systems can be correlated between cratons. Now, the cratons themselves have different geological histories. So that's, you know, there's a lot of supposition here, but the interesting thing is that if you have two cratons with a different history, and suddenly you see dikes that you think you can correlate of the same age between those blocks, then that's very important because it shows that the two cratons, let's just assume the Superior and the Hearn, were spatially separated. At some stage, they came together, the dikes injected across those cratons, and then they must have moved apart. So that kind of evidence suggests that there is lateral movement required to assemble and break apart disparate continental or disparate cratonic blocks. Now, the other piece of evidence that one can use are sedimentary basins. How? Why? Well, sedimentary basins can be traced across significant areas of craton. So here's the Pilbara craton in northern Western Australia, and the Fortescue group started to be deposited at about 2.5, and these black and stippled units can be traced across the southern margin and around the edges of the craton. So for over 500 kilometres, they can be traced, and so we know that by 2.7, the Pilbara craton was stable, it was subsiding uniformly, and the Fortescue group could accumulate. Similarly, in South Africa, the Transvaal group accumulates on the Kapvaal craton. So again, we have evidence for a stable craton. Now we can go into a bit more detail with sedimentary basins and look at subsidence mechanisms and what they might tell us and why they might be important. And so there are three major mechanisms by which sedimentary basins form. Extension, i.e. you stretch the lithosphere, it fractures through normal faulting, you might get some dikes even along those fractures, and then that rift, if it's successful and you form oceanic lithosphere, then you get thermal subsidence of that block and you get a passive margin succession developing along it. So that combination of extension and thermal subsidence is again good evidence for lateral dispersal of continental crust. Similarly, if you find a foreland basin succession where one block is loading another block and driving subsidence, again, that's evidence for one, lateral motion, and two, some sort of collision type processes. So the question then becomes, well, what are the oldest passive margin successions in the geological record? What are the oldest foreland basin successions in the geological record? And again, you know, these aren't always cut and dried. What I might call a foreland basin, you might disagree with. But taking other people's suggestions, the oldest passive margin type successions, in other words, the oldest rift to drift transitions, are present in these cratons and probably start around 2.7 type age, and certainly by 2.5 they become more widespread and present on lots of cratons. Foreland basin sequences, a bit more disputed. The oldest seem to be in the Neo to Mesoarchean type time frame. But the important point is such basins require lateral motion of continental blocks. Geochemical archive, particularly of mafic rocks, people have, certainly on the present day Earth, one sees various elemental abundances, or in more particularly elemental ratios, thorium, niobium, that are equated with fluid flux melting above a downgoing slab, producing high thorium niobium ratios. And people have measured similar type ratios in Archean rocks and said, well, therefore we have evidence for subduction. I'm not so sure, but let's just go with that. And so one can see that perhaps in areas of West Greenland, the North Atlantic, or in northern Canada, potential evidence for fluid flux melting. In 3.8 GA, in the Pilbara, there's a change from more within plate type character to more high thorium niobium ratios after 3 billion years ago. And then in the Yilgarn, more around 2.7. So we see evidence for at least localized and certainly episodic recycling of continental lithosphere or lithosphere to produce fluid flux melting, and possibly that's an indicator of subduction. Now, I've come back to this diagram with different compilations for the different cratons, and we talked about the dikes. Associated with the dikes are these sedimentary basins that we also talked about, and regional deformation events shown in yellow. So we see a kind of an orogenic history here for these cratons of stabilization in the late Archean. But of course, the history of the cratons goes back in time, certainly back to the Eo and Paleoarchean, and they show a very similar pattern. Now, the timing in each is slightly different, but the pattern is similar. And what's that pattern? It's a protracted granite greenstone terrain, felsic magmatism, mafic magmatism. Remember that bimodal silica content that we talked about early on. And that felsic magmatism tends to be TTGs, tonalites, strongymites, granodiorites, and they extend for up to hundreds of millions of years through these different cratons. So protracted periods of felsic and mafic magmatism. But then the final stages of each craton, there's a change. And there's a change in terms of a switch from more sodic type felsic magmatism, TTGs, to potassic granites. Potassic granites, potassic granites, potassic granites, which are relatively short, tens of millions of year type time frame. And they're also associated with these yellow bands, which are regional compressional deformation. Okay, so there are these patterns within the cratons that suggest there is a change in character of the crust and perhaps a change in tectonic mode. Structural styles. Pilbara's classic example of these dome and keel patterns in Archean cratons, big granite domes here shown in these lighter colors, high uranium, thorium, potassium type compositions, and then the intervening darker coloured greenstone belts. And here's a cross-section across them. Other belts, such as the Yilgarn, show much more linear trends with more narrow focus zones of deformation. And so for the Pilbara, we think there was a dome and keel structures. For rocks older than 3.1, then there is a significant change in the Pilbara at about 3 billion years ago. You saw that change I mentioned in the mafic geochemistry to more subduction zone type geochemistry. We see more linear type features develop in the Pilbara in its later history. So there seems to be a change in the character, certainly of that and some other cratons as well. Metamorphic patterns have also been used to build together a history of the early Earth. And the importance of metamorphic patterns is that they're essentially this global compilation of data. So remember I talked about local data sets trying to extrapolate global patterns from them. Well, the beauty of the metamorphic data is that we have this global compilation produced by Mike Brown and colleagues, and it's divided into three sorts dependent on the temperature and pressure components. And so you can have high temperature metamorphism, intermediate pressure shown in green, typical Barovian type environments, and then high pressure type features, which are really only present in the Neoproterozoic and Phanerozoic. But what Mike highlighted is that you see these temporal equivalents. So you see a pattern of high temperature and intermediate temperature pressure patterns around 2.7, 2.8, another around 2, 1.9, another around 1, and another at the end of the Neoproterozoic, and then more common through here. And they've been related to various supercontinent cycles, suggesting that they involve, again, lateral motion, regional compression, perhaps regional extension, to drive these sorts of patterns. The one potential problem with this data that I should highlight is that this is a temporal correlation, all right? So we've got, red points that are here around 2.8, green points that are here around 2.8 or whatever. We don't have a spatial association with this data. In other words, we can't say that this red point occurred laterally adjacent to this green point. This could have occurred in the Pilbara, and this could have occurred in Zimbabwe or something. So, we don't have that spatial association, which if you're going to talk about plate tectonics and the linking between different metamorphic patterns, one would like to see that spatial pattern developed. But when with time, we may be able to develop that, but we're not there yet. So that's just a caveat to add. The final bit of data I want to talk about in terms of compilations, etc., is perhaps the gold standard in terms of the modern Earth, in terms of the Phanerozoic paleomagnetic data to demonstrate lateral motion of the lithosphere. As we go backwards in time, of course, that becomes a real problem, mainly because the Curie point of magnetite is often surpassed in metamorphic conditions on the early Earth. So we have limited amounts of data. We also have the issue that we have longitudinal uncertainty with this data, as well as hemispherical uncertainty. So we don't know if something like this is the superior craton here shown in this red color, whether it lay in the northern hemisphere or the southern hemisphere at that time, as well as we're not sure of its longitudinal position. We know its latitudinal position, about 20 degrees north of the equator or 20 degrees south of the equator, but we're not sure of the latitudinal. So we have these uncertainties shown by these changing arrows here. What we can say is, though, with the limited data we have available, certainly by the Neo-Archean, the superior Kapval and Kola in this time frame show relative lateral motion. Similarly, the Kapval and Pilbara over this time frame show relative lateral motion. So good evidence for some sort of plate tectonic-like process operating. So what I've tried to highlight in those various slides is that there are major changes in the late Archean record. We certainly see that by the end of the Archean, good evidence for rigid lithosphere. We see evidence for differentiation of the lithosphere. We see changing compositions. We see evidence for, through metamorphism, through thickening of continental crust. We see the incoming of passive margins and fall-end basins into the geological record, evidence for lateral motion. We see evidence for at least localized fluid flux melting, which may be related to subduction. We see evidence for the incoming of globally paired metamorphic belts. We see evidence for linear compressional belts, and we see paleomagnetically constrained relative motion of cratonic blocks. So we see that sometime through the late Archean, in this 3.2 Mesoarchean to Neo-Archean 2.5 time frame, we see a series of changes. They're not all at once. They vary from craton to craton, but we see an overall change in character and style. And this brings back to the point that I said that if you're going to invoke these things as the incoming of plate tectonics, it's very hard to give a specific birthday for the start of plate tectonics. There's a transitional period through this time frame where these patterns start to emerge. As we go backwards in time to the very early Earth, understanding the patterns that are there become harder and harder because, like our duck, the rock record becomes more and more incomplete. And certainly prior to 3.8, we've got practically no rock record, and we're really constrained to just using the mineral archive, and in particular, zircons. And the Yilgarn, this is a compilation of data from the Yilgarn craton, has been particularly useful in that regard because we have the Jack Hills and the Narian terrains, which have zircons going back to about 4.4 billion years ago. And of course, we have the younger Yilgarn, and we have zircons going through the Archean itself. So this is important. We have a Hadean and an Archean record. And what you see here is that there is a dramatic change in the nature of the hafnium isotopic ratios in these zircons at around 3.8 billion years ago. And so those that are older than 3.8 basically lie below what we call Chur, and certainly below the depleted mantle line. So we refer to these as relatively evolved zircons. So they all lie on various lines that can be extrapolated back to around about 4.4. So what that means is that these zircons and the rocks they were in kind of sat in the crust and stewed. They just sat there. They were variously reworked. So here we might say we had a zircon that's got an age of around 3.8. So that's when the magma crystallized, but it was crystallization of a magma that had resided in the crust probably back since about 4.4. So we see this long history of reworking of magmas throughout the Hadean back to this earlier stage. But suddenly, at around 3.8, we see this influx of juvenile material that's come in part straight from the mantle or some mixture of mantle-derived and crustal-derived mixing between the two. So a dramatic change. Now, I'm going to confuse you. This diagram goes from oldest on the right to youngest on the left. The next diagram is a more recent compilation, and it includes, so here's the Yilgarn again. So that's basically the data I just showed you. But now the oldest is on the left and the youngest is on the right, but the pattern's the same. The older zircons, older than about 3.8, lie on this kind of mixing line going back to the early Earth. And suddenly at around 3.8, we see this influx of juvenile material, indicating we've got this mixing of juvenile and more evolved material. Now, all the cratons seem to show a similar pattern. The early data isn't always as good, but they all show at various times. And again, there's not a one time fits all. Sometime after 3.8, the Yilgarn's about 3.8. The Slave is more around about 3.6. We see a change. The North Atlantic, we don't have anything really older than about 3.8, but we see this influx of juvenile material. somewhere like the Singbom in India, we see older material, and then a change at around 3.5 or so to more juvenile. So at various times after 3.8 to about 3.2, we see a change from reworking of material within the crust to the influx of juvenile material. Okay, so that's some of the rock data. Incomplete, as I said. Numerical models have proved very useful in trying to understand what might have been going on the early Earth through these time frames of heightened mantle temperature. So we don't have much preserved, but numerical models can give us some insights into the processes that were operating through that time frame. And I've got three models shown here. I'm not going to go into detail. I'll mention this middle model in a bit more detail. But the upper one shows that what's interesting here is that you've got lithospheric extension and rifting, and that induces, obviously, magmatic activity, and you're forming depleted, relatively relatively rigid continental lithosphere by that process. The rifting in this early time frame of Earth evolution never progresses to the point of breakup of this bit of lithosphere. In other words, never to developing a passive margin. It starts to rift, and then the side of rifting jumps laterally and progressively keeps on jumping laterally as part of that process. So that's quite different to kind of the rifting we see on the Earth today. This paper by Priyadashi Chowdhury and others talks about peel back of orogenic systems. Again, there is a stretching of the lithosphere. We see things that kind of look a bit like subduction, but they're not subduction. It's a peeling back. It's not slab pull, it's a peeling back. And we get characteristics that look a bit like the modern Earth. We even get metamorphic patterns that look like the modern Earth, but it's not within a strict subduction-related type environment. I might skip that slide, and I'll go on to this one, which is a detail of that middle slide from the previous diagram. And this is a diagram or a model run by a PhD student of mine, Prashana Ganawandana, and this is a paper that's currently under review. And what it shows is that a system that, if just left to run, progresses from what we call a rift and drip stage into a rift and subduction type environment after about 1 billion years. Again, at high mantle temperatures. But what happens in this model is that these processes of rifting and drifting result in cooling of the mantle, and that cooling eventually allows a rifting and subduction type environment to develop. What's important as well, and it's not quite clear on this diagram, but I'll come back to it in a second, is that in this rifting and subduction type environment, we have a relatively rigid plate developed. So we rift the lithosphere, and as we move away from that rifting site, the plate maintains a constant velocity. In other words, it is rigid. In this diagram, in this earlier one where we've got extension and dripping, we have a rifting type situation going on, but the lithosphere in between is highly variable in its lateral velocity. And that indicates that it's being thickened and thin as it's moving laterally. So there's this broad zone of deformation, not a very sharp focused zone of deformation like we see in this diagram. So let's now start to bring this together and summarize what we have seen. And in that paper that I mentioned at the beginning of the talk, we divide the Earth into a number of periods. The proto-Earth prior to the moon forming impact, then from 3.45 to 3.8, what I refer to as the primordial Earth. And this is based on that mineral archive I showed in a previous diagram, where there is evidence for widespread crustal reworking, but limited evidence for juvenile crust. All right, so that's the kind of the key feature. Then in this period through the rest of the Archean. The first part, up to about 3.2, was where, in that diagram of zircon data, we saw the progressive incoming between 3.8 and 3.2 of juvenile crustal addition. So we saw lots of juvenile zircon, hafnium data, but that's also the period in which we get the large-scale TTG felsic crust forming. So that's the period of craton formation on the Earth today, the Pilbara, the Zimbabwe, the Yilgarn, the Superior, craton, etc. After that period, in the period from about 3.2 to 3.5, we saw evidence for craton stabilization, development of more rigid cratonic blocks. That was marked by a change in the nature of the magnetism, a termination of that TTG-type magnetism, which had been protracted throughout a lot of the Archean, and a switch to potassic felsic magnetism, potassic granites, if you like. It was the time for emplacement at the end of this of widespread regional dikes, of regional deformation across the craton, and subsidence of the craton and the development of sedimentary basins. So that really marks this subsequent post-Archean, Proterozoic and Phanerozoic history of rigid lithosphere and focus zones of deformation. So that's, I think, the significant changes. The question is then, what is the relationship to tectonic mode? I think I've hopefully tried to convince you that the switches, if there are switches, are probably transitional. And indeed, we may not have, because of that, we may have periods where more than one mode is operating at any one time. You could have, if you like, stagnant lid and squishy lid, or squishy lid and plate tectonics, or rigid lid operating together. And let's now jump back to this diagram, which talks about those sorts of tectonic modes. So we think one explanation for that data set that I talked about prior to 3.8, where we see reworking of material within the crust, no major juvenile emplacement of magma, mantle-derived magma into the crust or the lithosphere, could be represented by a stagnant lid type mode in which the mantle and the lithosphere are decoupled, and the lithosphere is essentially undergoing no significant surface velocity. So this type of environment here. Obviously, once we develop rigid plates, we start to develop linear belts, linear orogenic belts, which are probably indicative of original linear plate boundaries, just as we see today with linear plate boundaries, ridges, convergent plate margins, ultimately producing, through closure of ocean basins, alpine, Himalayan type mountain collisional belts, etc. So we see that type of relationship, constant velocity of the surface plate because it's rigid. In between these two modes, we have coupling between the convecting mantle and the lithosphere, but the lithosphere is still, because of high mantle potential temperatures, its rheology is affected by that, and it's deformable, and so we get broad zones of deformation represented by changing surface velocities, changing angular momentums. And this is just a diagram that tries to bring all of that together and shows this time. Here's time vertically here. So the proto-Earth, we had a magma ocean. The Earth was first accreting. Then once that cooled, we probably had perhaps a stagnant lid type environment. We can't rule out that there was some squishy lid type activity going on locally, or stagnant lid locally with squishy lid. After 3.8, I think we start to see more widespread squishy lid type tectonics, which is coupling between the mantle and the lithosphere, but that the lithosphere is continuing to show internal deformation through that coupling process. Eventually, the lithosphere develops into rigid blocks, and certainly after 2.5, but probably through this period, 3.2 to 2.5, we're transitioning into that active lit environment, and that continues with various changes through to the present day. So I think that's probably a good point to stop, and I'm happy to take any questions. I can try and expand on some of those issues if they're of interest to you, but thank you very much for your attention, and I hope that was of some interest to you.
Wait,
Catherine, you're on silent.
Yeah,
there you go.
yeah. I had some noise in the background, so I wanted to say thank you very much, Peter. It was a very interesting talk. And now we are going to open the floor to questions. So either you put it in the chat or you raise your hand and you unmute yourself and ask your questions. Any question? Okay.
Let me say, I don't know whether this will stimulate questions or not. You know, there's great uncertainty in those things I've talked to you about, and the reasons are obvious. From the duck analogy, there's limited exposure. And what happens is, you know, I'm sure you've seen papers, you know, you see them come all the time. Someone will say, well, plate tectonics started here because I measured this isotopic ratio, or something else. Someone else says, oh, well, no, it doesn't start there. It starts at another time because of this data set. What's important is individual data sets aren't good in proving or disproving anything in geology, indeed, and probably in life as well. You need to integrate all the available data to hopefully come with an answer, and that's what I've tried to do with that presentation there. But perhaps the other way of thinking about it is, if I think plate tectonics, say, started by 2.5, or someone else thinks it started at 3.2, or some people think it started in the Neoproterozoic, finding another piece of data that supports it started in the Neoproterozoic, or started at 2.5, or it started in the Paleoarchean doesn't help us. What you've got to do as the audience, I'm saying here, as researchers, as future researchers, is go out and look for evidence that disproves it started at 2.5, or the Neoproterozoic, or the Paleoarchean. You can never prove these arguments, you can only disprove them. And so we need to, that's why I say we need to incorporate as much data as possible. And we need to be critical of the data we do incorporate, and don't believe what we say. Both, I shouldn't believe what I say, but you, as listeners and as researchers, definitely shouldn't believe what I say. You should critically evaluate it and go out and hopefully develop your own ideas and your own data. Right, sorry. I see there's a question in the chat. Can someone read that out? Oh, here it goes. Thank you for your, oh, that's it. Thank you for your presentation. Okay.
Yeah. Any question? Okay, maybe I'll ask one for once I can ask a question. You showed these different numerical models, okay, with mimicking each mode of the plate motion or lead or static lead. Is there any numerical model that can go through the whole sequence from stagnant to plate tectonics, or?
They go through parts of it. No, none of them. I think this model in the middle is the first that's really, it starts off with essentially a single lithosphere across the top. So I haven't showed you 0 million years here for the model, but it starts off with a uniform thickness lithosphere, and then it progressively, self-consistently evolves into this rift and drift mode. And then into this plate tectonic type subduction mode. So it's, I think, quite good. This other model that I didn't really talk about starts off with a uniform bit of lithosphere across here, and we ran it twice at 2 different temperatures, 130 and 260 degrees C higher than the current temperature. Say we took 1350 as the current temperature and ran these higher ones, and they both ultimately produced the same result. The only thing we did to this model was we changed the thickness of the lithosphere on the right-hand corner, and that induced dehydration or induced melting in the mantle because of adiabatic decompression, and that induced dehydration stiffening. And so you started to produce, shown in yellow or yellowy green here, a stiffer bit of lithosphere, and that grew as the melting continued. And so that migrated laterally by that process. And so you started to produce, because of that lateral migration, you started to consume some of this material here, not necessarily by subduction. They were more drips, but they were drips that had a dip, if you know what I mean.
Yeah.
But what's interesting about the model is that it runs, okay, and this continues to grow, but it kind of terminates at this point. In other words, it doesn't grow any further. And on this side of the model, we just have a stagnant lid. We have constant thickness lithosphere. We have convection cells developing. We have a little bit of material downwelling in here, bit of change in thickening, but it's basically stable. So what's interesting about that model is that it's multimodal. So the one model develops into two sorts of modes on if you take this as the Earth, on the Earth at any one time. So after 800 million years, you could say half the Earth is stagnant lid and the other half is undergoing some sort of lateral motion of a lid. Now, exactly whether you want to call that plate tectonics or not, it's another matter. I wouldn't. But you can see, I suppose this gets back to the point I made, that the movement from one tectonic regime to another isn't global necessarily. You can have multimodal type behavior on the Earth at any one time.
But it's starting from the surface, right? It's not starting from something which
this one is indeed starting from the surface. Yes, indeed. But it's starting, I suppose, from the surface because of the overall hotter mantle potential temperatures. But yeah, good point.
I have a question in the chat. So it comes from Abigail Plimmer. Do you think that there is a potential for any evidence of earlier tectonic modes within the deep Earth, or is it likely reworked beyond recognition?
Okay. Who knows is the answer to that one. What I would say is, I think it's going to be very difficult, and I think they largely are reworked. But think back 20 years ago. I'm not sure of the age of all the audience or the age of Abigail, but you know, 20 years ago we had the Jack Hill zircons, and we knew they were old, that they were Hadean in age, but we didn't know anything else about them. You know, it was kind of an interesting little sidelight. You had these old bits of zircon, but suddenly we got oxygen isotope data. So multi-isotopic system data for them, and they showed that they had oxygen isotopic signatures that indicated that they had interacted with meteoric water. So that was a real revelation. It showed that the Jack Hill zircons, which had crystallized from some sort of felsic, presumably granitic type melt, or formed a granite, that granite had interacted with meteoric water. So at 4.4 billion years ago, there was water on the Earth. 20 years ago, we didn't really know that or appreciate that. So the word Hadean means hell-like, Hades. So, you know, that was the implication was that the Hadean was no hope of life. There was no water on the surface of the Earth. It was a very unpleasant place to be. But suddenly, 20 years ago now, we know that there was water on the Earth. Water on the surface of the Earth, a key ingredient for life. And we've done, you know, remarkable things, at least in terms of geochemistry and studying Jack Hill or early Earth zircons. I gave you that compilation of hafnium through the different cratons through time, how that could possibly be interpreted in terms of possible stagnant lid or and then the start of some sort of juvenile magmatism. So what we're going to find in the next 20 years, whether it be from zircons, whether it be from things we'll discover in terms of age or chemistry or numerical modeling. Most of the numerical models we run now are two-dimensional. Computationally, it's harder to do them at more than that, to get the resolution that we would like. I'm sure there will be vast improvements in numerical models through computing power. There'll be additional things we'll be able to analyze with higher precision, higher accuracy through mass spectrometry, further developments in mass spectrometry. Again, zircons, go back into the 60s or the 70s, we had great trouble getting reliable ages out of them. Then we developed ion probes, in part for the moon. We brought back these samples from the moon, from the Apollo missions. We didn't want to destroy them by crushing them up and dissolving the grains to date them. So we developed ion microprobes. And then, of course, we've developed ICPs and developing not only the age or the oxygen values of zircons. We're analyzing all different sorts of mineral phases now. We analyze apatites, we analyze rutiles, we analyze titanites, and we determine, their ages. We determine the link that they have back to the source magma from which they crystallized, or the metamorphic conditions under which they were experienced. So we're learning huge amounts, over the last 20 years, and I'm sure over the next 20 years, particularly for those of you that are students that are going to be driving some of this research, then we'll learn incredibly more to come. So, this isn't the end of the story. This is just one stepping stone along the story of understanding the way this magnificent planet we live on works. And, I draw the analogy that people like the medical profession, huge amounts of money are invested each year. I don't know, there's probably billions, trillions of dollars in medical research to understand one organism on the earth, a human. And we still struggle. We get a pain in our gut, we go to the doctor and the doctor doesn't really know what caused it, type of thing. So here we are, a few geologists with a few, pitiful amounts of research funding, trying to work out 99.99999% of Earth history, and the medical profession is working on one component of that present day history, and still struggling. So, there's lots to be discovered about the Earth.
I think so. Okay, any other question or in the chat or no? Shall we stop here? I think so. Okay,
Right.
So Peter, thank you very much for this talk and challenging everyone to tell us more about the Earth in the next few years.
Right. I enjoyed it, and I hope you did. And feel free, any of you, if you think of a question, to email me at some stage. I'm more than happy to hear from you. So all the best, and thank you very much.
Thank you all, and thank you for joining us.
Okay, see you. Bye.
Bye. Thank you, Peter.